Hello everyone, it's Dr. C. What I'd like to do in this video is talk about solution stoichiometry. So I want to remind you that, stoichiometry is really stoichiometry. It's all about what I have showing in front of you there. It's all about moles. Okay, so if we have moles of some substance in a balanced equation, whether reactant or product, we can use the mole ratio to go to moles of something else in that balanced equation. And that really is what stoichiometry is all about. It's using the mole ratio in the balanced equation to go from moles of one substance in that equation to moles of something else in that balanced equation. Now, let me remind you that the type of stoichiometry we've worked so far. A lot of times we would start with grams of substance. Okay? A lot of times we were dealing with solids. And so if we have a solid, the way we would measure out that amount of substance would be to weigh out its mass, typically in grams. So you might have to convert to moles first. And we know how to do that, right? Yeah, we would use the molar mass of the substance to convert to moles. And then we would apply the mole ratio to get to moles of something else. Now the problem might ask for grams of that other substance, say grams of product. Well, we could easily go to grams, right? Say it was gram. The problem asked for grams of product. We could easily go to grams of product. And again, we would need the molar mass of that substance to do that. All right? So I have videos posted that have stoichiometry with grams to moles, moles to grams. So you could look at those if you need to refresh that. But we're talking about solutions now. So how do we express the concentration of a solution typically in chemistry? Yeah, we use molarity. Okay, molarity, as shown here, is mole solute per liters of solution, right? Because we're typically looking at two-component solutions where we have a solute and a solvent, and those two things make up the solution. Okay, so we have to express both the amount of the solute, which is right there, and then the solvent is part of the solution. So we have both our components in the molarity. All right. So if we're thinking about moles and we're thinking about molarity, well, here's our moles in that equation. So we can always solve for moles solute if we need to. And how would we do that? Well, we'd have to rearrange this equation. We'd multiply both sides of the equation by liters. Liters on this side would cancel. And make sure you know this, moles of solute is going to equal to molarity times liters. Okay, very useful to know. So for solution stoichiometry, you might start off with a solution where you know the molarity of the solution and you know the volume of the solution. Now it might not be in liters to start, it might be milliliters, but you could take care of that. And then we can get the moles that way. Okay, so rather than converting grams to moles, for solutions a lot of times we'll have to take molarity times liters to get to moles. And then we again apply the mole ratio once we have that to get to moles of something else. Now at that point, the product might be a solid that precipitates out a solution. And we might want to convert to grams, which we could do. Or we might want to know the concentration of some unknown solution. All right. So if we want to get the molarity, the concentration of that unknown solution, we would need, sorry, this is a little messy, both moles and liters. Well, we would have just solved for moles here, and the volume of the solution would have to be given somewhere in the problem. Sorry about that. I wrote way too close to that other thing there. Okay, so you need to be flexible when solving stoichiometry problems. All right, and again, keep in mind, I need to get to moles so I can get to moles of something else in that equation. For solids, I'm going to start with grams typically. For a solution, I'm going to use molarity and liters to get to moles. All right, let's practice this. Let's practice this. So here's a problem. So we're going to react 75 milliliters of 0.15 molar KCl solution. Okay, so that's here in the equation. So I make double check that that equation is balanced because you do need a balanced equation. So we're going to react the KCl solution with an excess of lead nitrate. So that means we don't really have to worry about the amount of lead nitrate. Okay, that's an excess. What mass of product lead chloride? Now, lead chloride is going to precipitate from that solution. It's going to come out as a solid. So we could then filter that solution, collect the solid, dry it, and then weigh it out, see how much we get. Okay, so what mass is going to be produced? So how do we go from amount of KCl to amount of lead chloride? Yeah, we have to do that in terms of moles. Okay, so we know quite a bit of information about KCl, and we want to get to our product, lead 2 chloride. All right, so the way that we're going to get from KCl to lead 2 chloride is in terms of our mole ratio. There's the stoichiometry piece. Now, we want grams. We can do that once we have moles of lead 2 chloride. But we don't have moles of KCl to start with. What do we know about the KCl? Yeah, we know its molarity and we know its volume. Now, it's in milliliters, but we can convert that to liters, and then we can get to moles of KCl. All right, so again, remember this piece, moles to moles. I know enough information about the KCl to get to moles of KCl, then I can apply the mole ratio to get to moles of product in this case. I don't want moles of product, but I can convert from moles to grams pretty easily. All right, so let's do this calculation. Okay, molarity times liters is going to give us moles of KCl. So we have 0.150 moles of KCl per 1 liter of solution. I'm going to abbreviate solution, SOLN, times, now we need to multiply by the liters. Now a quick way to convert milliliters to liters is just to know that milli means 10 to the negative third. All right, so we're just writing the number instead of the letter. You can punch that in your calculator as 75, use your scientific notation key, 10 to the negative third, and then it'll work out. Now you could convert that, and I believe you would get 0.075 liters. All right, so that is going to give us 0.01125 moles of KCl. So there we go, we're at moles of KCl. Now that we have moles of KCl, we can get to moles of anything else in this equation. But we want to get to moles of PbCl2. So we're going to use the mole ratio to get to moles of PbCl2, and then we can get to grams. So let's do those next steps. And I'm actually carrying, oops, sorry. Let's try that again. I'm carrying an extra significant figure here to avoid rounding errors. In the balanced equation, we noticed that there is a 1 in front of, PbCl2, 1 mole PbCl2 for every, and note the 2 in front of KCl, 2 moles of KCl. And I'm going to go ahead and work this stepwise, but you could, of course, then just add the molar mass as a conversion factor on here and just do one calculation. Let's do this step by step. That gives us 0.005625 moles of PbCl2, lead 2 chloride. And then the last step, we don't want moles of PbCl2, we want grams. How do we get from moles to grams? Yeah, we need the molar mass. And so look at your periodic table, look up the molar mass of lead, look up the molar mass of chlorine, multiply that by 2, add those together, and you should get about 278.1 grams of PbCl2 and 1 mole of lead 2 chloride. All right, I forgot to cancel my units above, but as you notice in the first calculation, moles of KCl cancel. We set up the second one, so moles of lead 2 chloride cancel, leaving us grams. And we end up with, and we really only had 3 sig figs to start, 0.150 and 75.0 milliliters. So now I'm going to round to 3 significant figures at the end. 1.56 grams PbCl2. All right, so there we go. So let's just scroll back up and look at the problem again, just to refresh our memories. So we reacted 75 milliliters of 0.15 molar KCl. From that information, we were able to calculate moles of KCl right here. Then we were able to do what I consider the real part of stoichiometry, the mole ratio part, to get to moles of PbCl2. We didn't want moles of PbCl2, however, we wanted grams. But we know we have to get to PbCl2, lead 2 chloride. We get to moles first. Then the last part of the calculation is to use the molar mass to get to grams. All right? So, a little bit more complex than just grams to moles, I guess, but it's the same thought process. And I will try to convince you that stoichiometry is stoichiometry. Later in the semester, we will actually talk about gases, where we'll typically talk about pressure, volume, and temperature of a gas, and that we're going to use that to get to moles. Okay? But stoichiometry, we need to get to moles before we can get to moles of something else. All right, let's do one more example problem that I have here. Okay? So this one's a little bit different. Let's see what we have here. We have 10 milliliters of H2SO4, sulfuric acid, that's unknown concentration. All right. We then titrate it with a solution that we know more about. We have 1 molar sodium hydroxide, and it takes 40 milliliters of sodium hydroxide to neutralize the sulfuric acid. What is the molarity of the H2SO4 solution? All right. So we don't know the concentration of the sulfuric acid, H2SO4. We want to figure that out. So we want to solve for molarity. What do we need to solve for molarity? We need two things. Yeah, we need moles of H2SO4, and we need the volume of that H2SO4 solution. All right, so this is what we want to solve for. Okay. Do we know either moles or volume of that H2SO4 solution? Yeah, we know the volume, 10 milliliters. All right. Now, we need liters. That's not a big problem. We can convert from milliliters to liters. So what do we need to find to be able to calculate the molarity of the H2SO4 solution? Yeah, we need to calculate moles of H2SO4. Well, how are we going to do that? I know you're thinking ahead. We need to do some stoichiometry because we know the molarity of the sodium hydroxide solution that we're reacting with that H2SO4. We know the volume of that H2SO4 solution. It's not in liters, but we can convert that. So what can we calculate? Yeah, exactly. Moles of NaOH. Once we have moles of NaOH, we can apply the mole ratio to get to moles of H2SO4, and then we can calculate the molarity of that unknown solution. Sound like a plan? Now, one thing that I didn't do in this equation is I did not do a very good job with significant figures. So let's assume we have 3 significant figures in these numbers to carry through this calculation. All right, so we need to get the moles of sodium hydroxide first. Let's do that. We have 1 mole of sodium hydroxide per liter of solution, 1 molar sodium hydroxide, times, let's do the same thing for milliliters. Let's write 3 sig figs here. All right, let's see what we get there. Oh, that's just going to give us, because it's 1 times. Let me just make sure I get this right. Yeah, so we're going to get 0.0400 moles NaOH. All right, now that we have moles of that, we can now get to moles of anything else in that equation. Well, we want to get to H2SO4. So let's do the mole ratio to that. And again, you can string these together for illustration purposes. Sorry, I forgot to cancel my liters there. Look at your balanced equation, coefficient of 1 in front of H2SO4, coefficient of 2 in front of sodium hydroxide. Moles of sodium hydroxide cancel. And we have 0.02 moles H2SO4. All right, almost there. We now have moles of H2SO4. We know the volume is 10 milliliters. We can convert that to liters. We know moles and liters. We can get the molarity of that H2SO4 solution. Okay, 10 milliliters. All right. There's the concentration of that unknown H2SO4 solution. All right, so let's review this calculation again very quickly. First thing I would look at is, look at what you want to solve for. We want to solve for molarity of that H2SO4 solution. So we need moles and liters. We have volume, but we don't have moles. And this is where the stoichiometry comes in. We know the molarity of the sodium hydroxide. We know the volume of the sodium hydroxide, so we can get moles of sodium hydroxide. Now that's not what we want. We want moles of H2SO4. But this is where the stoichiometry comes in. We can then, once we get the moles of sodium hydroxide, we can then apply the mole ratio here, 1 to 2 mole ratio, to get the moles of H2SO4. Now we have what we need to get to molarity. We have the moles of H2SO4, we have the volume of solution. We can now calculate the molarity of that unknown H2SO4 solution, moles divided by liters, and we find that it's 2 molar. So that's solution stoichiometry. Practice these. They're, I think, a little bit more challenging. Students typically have more trouble going from molarity, using molarity in liters to get to moles rather than converting grams to moles. Right? And then, as you can see with this problem, we want to calculate the molarity of this unknown, so then we have to think a little bit more. We have to think, okay, to do that, I need both moles and liters. What do I have? Oh, I have volume, so I need moles. How am I going to get those moles? Oh yeah, I'm going to do stoichiometry. I get the moles of something else first, and then I can get the moles of what I want. Okay, so there's a little bit more thought that has to go into these solution stoichiometry problems compared to ones dealing with just solids where we're dealing with mass and moles. All right, practice these. I hope this helps. Have a wonderful day. Take care.